Now, when talking about circuits, we've defined two concepts so far. Voltage, which is the pressure or the push behind the charge. That's what gets it moving, right? That's what we get out of our batteries. And now current. And that is the actual movement or the flow of charge, or the electrons actually moving through the wires or the conductors. And the last thing the third concept, there's three of them that we need to talk about, it's a new one, is what gets in the way of this charge, right? What gives it something we call resistance. So depending on what you put in your circuit, you're going to have a different amount of resistance to the flow, something that's going to slow things down. And that can be various things. Everything you put in a circuit adds some element of resistance, some more than others. Right? So this quantity of resistance is a physical property. Of an object or material to slow or impede the flow of charge. So charge cannot move easily through that. Now, the flow of charge would be what we call current. All right, so if things can't move easily, I hope you're thinking, hey, insulators, right, would be giving a lot of resistance, and that is true, right? Insulators have very high resistance. Now, in a circuit, throwing an insulator in the way, it's just probably going to stop the circuit, right, because charge can't flow in an insulator. And so most things that are applying resistance in a circuit aren't quite insulators, but they aren't the best way to conduct that flow, right? And so resistance has a unit. The letter is R. R is what we use for resistance, and it's measured in a unit called an ohm. All right, in the plural with the S on there, ohms, O-H-M-S. And the letter we use for the unit is a Greek letter omega. Looks like a horseshoe. And so the Greek letter omega. Again, continue with the trend of weird letters relating to some of these topics, right? So instead of R being the unit for resistance, R is what we describe resistance, but the unit itself is called an ohm, and we use this omega symbol. Right? So we talk about resistance in a circuit. Our light bulb is a resistance in that circuit. It slows things down. Right? So anything that we're trying to power in this circuit, the thing we call the load on the circuit, the loads, for example, the light bulb, or really any appliance that we're trying to run, something we have plugged in to our circuit. These are what we call loads on the circuit, and each of those are going to have some amount of resistance. Sometimes we say they have an internal resistance. They aren't really designed only to slow the charge. It's just in order to make those objects do what they're supposed to do, produce light, run some machinery, it's going to slow charge in doing so, right? It's that transfer of energy, right? So it's this internal resistance that exists that slows the current in the circuit. So loads have internal resistance that slows the current or the flow of the charge in this circuit. So again, anything you put in that you're actually trying to power, you have to factor in that it is going to have resistance in the circuit. And even the wires themselves can have some resistance. right? So a wire, which is actually made out of a conducting material, so by definition, it should not add much resistance, right? Conductors allow free flow. Wires do have some resistance, but they have a very low resistance. But if you have enough wire length, or if the material isn't the best material, for example, gold is the best conductor, or one of the best, but if you use copper instead of gold, and you have a 3-meter long wire, well, then you're going to have more resistance in the copper wire than you are the gold wire, and that's where you get some signal loss, right? And if you have a nice big fat wire, it's going to allow charge to flow easy. Think of like a big pipe will allow water to flow. Whereas a thin wire is going to add more resistance, right? So one thing to think about with wires is that if it's a thin wire or if it's a really long wire, you're going to have a scenario where you have higher resistance or more resistance. It's got more length to travel, or it's got to squeeze through a tighter window, right? A tighter cross section if it's a thin wire, right? Whereas if you have a nice thick gauge wire or a really short wire, you don't have to send it that very far, you're going to have lower resistance, right? So if you have like audiovisual cabling and you've got to run a cable to your TV, well, you better have that source close to your TV, like right underneath it if you want a good signal. Otherwise, you better get a really good conducting wire so that you don't lose your signal. So if you're running from your receiver up to a TV on the 3rd floor, you might lose some signal when you're sending it upstairs if you don't have a good enough wire. Right? And the third thing, right, other than the load and the wire itself, is something we call a resistor. This is actually a circuit element, and by its name, I hope you can make the connection that it applies a resistance, right? It's a circuit element designed on purpose to control or slow the current. It's a circuit element that is designed, and what it really is just a coiled wire wrapped in some kind of ceramic to manage the heat. Right? So it's designed to control, or by controlling, they're really just slowing the current. Right? So these resistors are in a circuit, and usually you'll see them, if I have a circuit diagram, they have a symbol that looks like this. It's this jagged line in here. And really that represents just a long wire, right? We talked about long wires are more resistant. So if I create a really long wire, then it's going to slow the flow down. And so that's really what happens with a resistor. Usually it's just a coil of wire, and that makes the pathway that has to travel a lot longer, right? So you get this idea of having more resistance, right? And so really we have 3 elements in a circuit now that we've defined. We've got voltage, current, and resistance. And I just want to show you real quick before we move on. I want to show you a circuit here again. So right now this circuit has a voltage, a power supply. That's the battery. That's what's going to give the push. We're measuring the current. We got a load, a light bulb, which has its own resistance. If you look on it, look at its resistance, 5 ohms. Right? So if I close the switch, we get a certain amount of current. We get 0.3 amps. If I lower the resistance of my light bulb, the current goes up, right? There's less resistance to the flow, so the flow should go faster, right? And so you see it going faster and faster. If I have higher resistance in that bulb, right? So I'm doing a couple things. Either I'm making that filament in that bulb either longer or I'm making it thinner. I'm getting a slower flow. Now the other thing I can do, let's take this bulb back to something where we're getting some decent flow. Now, let's say that bulb is designed for a specific amount of flow. If it has too much, it might burn out. Well, if that's the case, then if I'm designing this circuit, I might throw something in the way, right? This thing that I just threw in there, if I cut my circuit open, is what we call a resistor. It is a circuit element, right? And we can throw that in the way, so the charge has to go through this resistor. And now, with this resistor in play, it slowed everything down, right? So the current slows down in this resistor, and now we have less flow here. If I click on this, you'll see this is a 10 ohm resistor. And if I make it less, all right, you see the current is increasing. It's now 0.3 amps, right? And I can increase the resistance and the flow slows down. The other thing that's interesting to note, look at the colored bands on that resistor. If we're in class, we actually do some labs where I actually put these in your hands. We can look at some images of these. But the way they determine the amount of ohms that they're rated is with this colored band system that allows you to identify how many ohms they are. Right? And if I put a big enough resistor in there, a lot of ohms, look what's happening to the current. Right? As I increase that resistance, I'm getting almost no current. Look at the light coming out of this bulb. Right? The charge is almost not flowing at all, so you get no light. But as I lower the resistance, I start to get the light bulb to work again. So you get this sense of controlling the flow to increase or decrease the light. Anybody have a switch like this in your home? Anybody have a dimmer switch? Well, it's really just a variable resistor in there that you can change the value of as you rotate your knob, and that allows more or less flow to go to those bulbs, right? So it's a basic way to have a dimmer switch. You throw this resistor in there that you can change its value. We'll talk about how some of those work. All right, so we get this idea. We now have three concepts. We have voltage, right? Here's a 1.5 volt. Give it a little bit more pressure, and look at my light bulb get really bright, right? We have current measured with an ammeter, right? And if I give it more push, that current goes up as it gets brighter. You see some relationship here, and we'll play around with this. And then we have this idea of a resistor. And every element in here has resistance as well, right? So you have some resistance in here. And these wires, they don't have resistance for this thing here, but you can actually increase the resistance of the wires themselves, right? And that's basically making them longer or thinner. You can actually have resistance in the battery itself. So we won't get into battery or wire resistance much, but it is a concept you need to understand. All right, so hopefully this idea of resistance is something that makes a little bit of sense now.